right, let's take a look at our last problem, which is problem 2, and it's problem 12.2 from the course text, in which we're going to have an example in which we're going to compute excess enthalpy using tabulated data, partial molar excess enthalpy, and yeah. So the problem asks us that, or tells us that in the table below, we're given the enthalpy of benzene heptane solutions at 20 degrees C in 1 bar as a function of the mole fraction of benzene. A, we're asked to calculate and plot the excess enthalpy at 20 degrees C in 1 bar, so at the same temperature and pressure. And then in B, we're asked to calculate the partial molar excess enthalpy at the same temperature and pressure, and we're given a specific composition. So let's go ahead and let's look at part A and B first, and then we'll move on to C and D. Okay, so in A, the question at hand is essentially given this tabulated data, okay, which is all at a temperature of 20 degrees C and a pressure of 1 bar. Go ahead and calculate the excess enthalpy. Well, the key is, remember that my excess enthalpy is just equal to delta H of mixing, right? So I'm mixing pure components at constant temperature and pressure. So delta H of mixing would be equal to the enthalpy of my final mixture minus the molar average of those pure component systems I'm mixing together. So in this case, I'd have H minus x1 H1 plus, for x2, I'm going to write in 1 minus x2, or 1 minus x1 H2. Okay. All right, do I have H1 and H2? Yes. All right, so if I look up here, so when x1 is 0, that means x2 is 1. That means pure component 2. And so this would be equivalent then to H2. When x1 is 1, that's pure component 1. My pure component limit would give me H1. Okay, cool. And so if I'm thinking about, say, setting this up in Excel, okay, so if I were to take the data provided and tabulate it up, so here I have x1, here I have H in joules per mole, okay, where I'm going from 0 to 1. So in row 1, this enthalpy would give me H2. And down here, pure component limit in the other extreme, this would give me H1. I could use those then to go ahead and calculate HE, which would also be in joules per mole. Okay, cool. All right, and that's how I would get A. Oh, and then if I wanted to plot it, well, once it's tabulated, I would just plot HE versus x1. Okay, cool. So that's A. Now in B, it says calculate the partial molar excess enthalpy at x1 is 0.2, 20 degrees C in 1 bar. All right. So I suppose then we could tackle this in a couple of ways. Okay. Let's start with option 1. Okay. We're going to go say option 1. Okay. Which in this case may or may not be the easier way. Okay. And option 1 is only going to be applicable for binary systems. Okay. And so basically what I want to calculate is h bar 1e at x1 is equal to 0.2. Okay. And so for binary system, what I'm going to do is I pulled up our notes from chapter 9. So remember, chapter 9 is where we derived all of these cool expressions for mixtures. Okay. And we found that for binary system, we could obtain these simplified expressions for calculating partial molar properties using our intensive expressions of our property of interest and derivatives with respect to mole fractions. So if I wanted to apply that here, okay, I would have the h bar 1e, okay, is equal to, okay, so essentially F just gets replaced with HE, right? F is an arbitrary thermodynamic state function. So this would be HE plus x2, and it's a DHE dx1. And let's see if I completely mess this up. x2 df dx1. Yeah, so I have it. Okay. So then it's a matter of, well, how would I compute this? Okay. So this, right? So this is going to be at x1 is equal to 0.2. Okay. So HE, so I need HE at x1 is equal to 0.2. Okay. From the tabulated data, okay, we have an entry at x1 is equal to 0.2 for h, so I know we'll have HE there, right? So I have this. Okay. So this is x2 is 0.8. I have that. That's not a problem. So the only thing that I really need to worry about computing then is DHE dx1. So I need the derivative of HE with respect to x1 at x1 is 0.2. Okay, and so, you know, one way to calculate it would be I could fit, say, an analytic equation to my HE versus x1 data, and then once I fit said analytic equation, then I could just differentiate it and evaluate the derivative at x2 is 0.2, right? And so in theory, that might be the best way to fit it. You could fit, you know, essentially a Rudder-Keister type of expansion, XE, or HE. The other way you could do it is, given that tabulated data, is I could approximate this, you know, numerically. So I could use, say, forward finite difference, backward finite difference, center finite difference. But the trick of it would be that if I wanted to estimate DHE dx1, that's approximately equal to, say, delta HE over delta x1. So I might evaluate this as HE at, so let's just use forward finite difference. So I visit HE at x1 is 0.22 minus HE at x1 is 0.2 divided by, so this would be x1 at, so let's just do 0.22 minus 0.2, 0.02. Okay, so it's just x1 at 0.22 minus x1 at 0.2, which is 0.02. And so, you know, and if we were to assume that HE is linear, right, over this region, well, then that would be a, you know, reasonable estimate of the derivative at 0.22. Backward finite difference would have been, you know, say HE at 0.22 or 0.2, you know, minus the value at 0.14, and then the denominator would have divided by this minus that, right? So you could have gone backwards. Center finite difference would be, you know, essentially using these two neighboring points. Okay, or you could use a fancier way to approximate derivatives, where maybe I'd fit a Hermite cubic interpolating polynomial between, say, these three data points, and then, you know, evaluate the slope at 0.2. All right, so there's lots of different ways you could do it. But it would just be a matter of estimating that derivative, which I could do using, you know, say, simple numerical method in this case. Then once I have that, then I could just go and plug it in and directly compute h bar 1e. Okay. Option 2, which is a little more difficult. Okay. Okay, would be that, you know, I could use the definition that h bar, say, 1e would be equal to the differential of n HE, so the differential of the extensive excess enthalpy with respect to the moles of your species of interest, keeping everything else constant. Okay, and so the key there would be you'd have to assume a basis, right? And so if I wanted to evaluate that from the data above, you know, the trick is when I differentiate, say, moles of species 2 is being held constant, right? So I could, you know, take, say, N2 to be equal to 1. Okay, and so if I just say that N2 is always 1, then you'd have to go through in your tabulated data, and since you know X1, and if N2 is always 1, okay, so then how do I get the moles of species 1? Well, x1 would be n1 divided by n1 plus n2. Okay, so if n2 is always 1, and I want to solve for n1, well, let's see. So I have n1 is equal to x1, n1 plus n2. n1 is equal to x1, n1 plus x1, n2. So if I bring this animal over, then I have, okay, let me continue this over here. If I bring that over, I have n1 times 1 minus x1 is equal to x1 and 2. So therefore, n1 would be x1 divided by 1 minus x1 and 2. Okay, so if I have, say, my Excel sheet in which I have x1 and HE, okay, then I can go ahead, and I've assumed a basis of n2 is 1, so I can calculate n1. Okay, n2 is fixed, right? It'd be up in some reference cell. Then once I have n1 and n2, I could calculate n. Once I have n, then I can calculate my extensive excess enthalpy. Okay, this is going from 0 to 1. I have 0.2 at some point in between. Okay, bam. So I have that tabulated. And then it would just be doing the same trick where I need to numerically approximate this derivative, right? So then, you know, h bar 1e would be approximately equal to delta n he over delta n1, right? Everything else held constant, tp and n2, which is what I would have in this tabulated data set. Okay, and I want to evaluate that at, you know, x1 is 0.2. So I would need to do finite difference, you know, around this point. So whether it's forward or backward finite difference, you know, from this now marked up data set, I could go ahead and extract the data I need to perform said calculation. So if I were to do forward finite difference, so this would have been, say, x1 is 0.22. All right, so I could use these two rows. I could get NHE at those 2 points, and then I'd have to work out what delta N1 is. Okay, but you go ahead and use that, and that should give you the same exact answer. Okay, so that's option 2, and that would be in general for a multi-component system. All right, so that would be A and B. C, calculate the heat that's released or absorbed when 10 moles of benzene is mixed with 40 moles of heptane isothermally at 20 degrees C in 1 bar. Okay, so the key to this is, remember delta H of mixing, right? Our property changes upon mixing, right? We're mixing at constant temperature and pressure. So temperature and pressure here is still this 20 degrees C in 1 bar, right? So we still have our pure component systems at 20 degrees C in 1 bar that we're mixing to form a final mixture at 20 degrees C in 1 bar. So now the significance of delta H of mixing was that delta H of mixing is equivalent to the heat that must be added or removed from my system to maintain that constant temperature. Okay, so all I would need then in C is C, I just need to calculate delta H of mixing, so that'd be intensive, and then I would multiply by N. Okay, so let's do it. So benzene component 1, so N1's 40, no, N1's 10, N2 is 40. Okay, so let's keep track of this. N1's 10. So if I have C, N1 is 10, N2 is 40. Okay, so X1 then would be, well, let's say then N, which is N1 plus N2. Okay, that'd be 50 moles. So I have 50 moles. Okay, X1 would be N1 over n. So it'd be 10 over 50. So it'd be 0.2. We're still at this magical composition of 0.2 mole fractions. Okay, so Q, okay, my molar Q, my intensive Q, would just be equal to delta H of mixing, okay, since everything's at the same T and P, which in this case would be equal to HE at 0.2, all right, and that would have been tabulated in A, right, so I'd have HE. And then basically it's just asking for, the extensive quantity, and so if I want extensive, then that'd be NQ, which would be NHE, where N is just 50. Right, so I'd go ahead and multiply by N. Okay, so that would be C. Calculate the heat that is absorbed or released. Well, if Q is positive, that means heat's going to be added to my system, so it's going to be absorbed. If Q is negative, that means it's exothermic, heat's being released from my system. Okay, cool. Which brings us to D. So D asked us to calculate the temperature change when 10 moles of benzene is mixed with 40 moles of heptane adiabatically. So adiabatically would mean Q is equal to 0 at a pressure of 1 bar if the initial temperature is 20 degrees C. So the initial temperature is the temperature of those two pure component systems that I'm mixing. But now I'm going to assume that no heat's being added or removed from my system, so the mixing's being done adiabatically. All right, let's give it a try. So this one's a little more complicated, okay? But the key is still going to be, let me go ahead and add another piece of paper. New page after. Okay, so we don't run out of space. Okay, so let me just start here. So if I start with D, okay, the trick is still going to be my heat, Q, is still going to be equal to delta H. Okay, so as long as there's no work being done on or by my system, my first law of balance for this open system would still be Q is delta H. Okay, so the key is going to be calculated. Oh, and Q, right, since this is adiabatic, is 0. So delta H is going to be 0. Okay, well, what is delta H? Okay, well, delta H would be the enthalpy at, say, this final temperature, okay, minus, okay, so this would be molar, so it would be X1, H1 at T naught, okay, minus X2, H2 at T naught. Okay, so this is just because I'm working in terms of intensive quantities. So the change in enthalpy for my system would be the final enthalpy of my mixture at my given temperature minus, okay, so this is intensive, minus molar average of those pure component systems I'm mixing together at temperature T naught. Okay, so this looks essentially just like delta H of mixing. So remember when I wrote it down in its extensive form, right, it takes the simple form of an enthalpy balance. Here it's just intensive. If you were to multiply through by N, that'd be NH, N1H1, N2H2. Okay, well, that's a plus. Okay, well, then the trick is going to be, well, if I look at H, what is H? Okay, well, we can approximate H of T. Okay, so we're just given simple CP expressions. H of T I could write as being, say, some H. We'll write as H at T naught plus H at T minus H at T naught. Sorry, that's my phone ringing. Sorry. So I write H of T as H at T naught minus or plus H of T minus H of T naught. So I add 0. y. So I can take this. Okay, this is just a delta h expression. Well, why would I write it as this? Well, sorry, the phone got me a little flustered there. So let me pause for a second. Okay, so I'm going to take h of t, and I'm going to rewrite it as h of t naught plus h of t minus h of t naught. Okay, so now I can just work on each of these terms individually. Okay. Oh. So, sorry, you gotta give me a second. Yeah, okay. So, if I do that, I'm going to take this in 2 steps, just so I can take it piece by piece and have it make sense to what I'm doing. Okay, so delta h, if I plug this in here, so now I'm going to have this first term, which is h of t minus h of t naught. Okay, and then, so this term, so then plus h of t naught minus x1 h1 t naught plus x2 h2 t naught. Okay, so now I do that. Okay, this is just going to be delta h of mixing, or he, right? Since this is all at the same temperature. Okay, so I'm just trying to take this in piece. So right now I've got delta h then would be h of t, the enthalpy of my mixture at my final temperature, minus h at t naught, okay, plus he, okay, which I have, right? So I have he at that composition. So if I come back up here, all right, what are we given? We're given the heat capacity of our pure liquids. Okay. Okay. Okay, and so remember, we're ultimately looking for when delta h is equal to 0. Okay, so h of t minus h of t naught. All right, how the heck are we going to handle this? That's a good question. Well, let's just expand these things out and see what we can simplify. Okay, so h of t, I could equivalently write as x1 h1 at t plus x2 h2 at t plus delta h of mixing. Because delta h of mixing is this minus that. So this would be plus delta h of mixing, or I'm going to write it as he at t. Okay. Well, h at t naught then, I could write equivalently as x1 h1 t naught plus x2 h2 t naught plus he at t naught. All right, remember this is he at t naught up here. Okay. All right. So if I do h at t minus h at t naught, then I could write that as x1 h1 at t minus h1 at t naught plus x2 h2 at t h2 at t minus h2 at t naught. Then I have plus he at t minus he at t naught. Okay, and so if I do that, let's take this, one piece at a time. So ht minus h at t naught. So h1t minus h1 at t naught. Okay, I can just approximate that as cp1 t T minus T naught plus x2 CP2 T minus T naught plus I have this HE at T minus HE at T naught. Phew. All right, so if I plug that in up here, I have that delta H is equal to x1 times CP1 T minus T naught plus x2 CP2 T minus T naught plus HE T minus HE T naught, and then I had plus HE plus HE of T naught, and that's equal to 0. Okay, well technically these two HE of T naughts cancel, and I'm left with x1 CP1 T minus T naught plus x2 CP2 T minus T naught plus HE at T is equal to 0. Alright, so now in order to solve this, okay, we know our composition, so we know x1 and x2, we know CP1, we know CP2, we know T naught, alright, that's a 20° C. We're asked to solve for T. Okay, so in order to solve this, I also don't know HE at T. So what I'm going to have to do is I'm going to assume, I'm going to assume then that this is approximately equal to HE at T naught, okay, because HE at T naught, we calculated that in part A, so I could look up the excess enthalpy of my mixture at that given composition at T naught and plug that in. Otherwise, I don't see how I could solve it. So what I think what we need to do is if we take this final working expression, if we work up to it, which should be correct, I'm going to have to assume that my excess enthalpy at my temperature is approximately equal to that at my final temperature is equal to that at my initial temperature, so I can use that value we have. Then with my CP expressions, right, the only unknown would be T. Right, so I think we would make that assumption or approximation and then solve for T. That would give you a single equation with a single unknown. And so, give you a little more idea of this. So essentially you could say that HE at T is equal to HE at T naught plus a CPE, T minus T naught. All right, so we're essentially assuming that this term is 0. Okay, so if the temperature change is small, then that's reasonable. Or if the excess heat capacity is small, or negligible, or approximately equal to 0, it'd be equivalent. So you're assuming the excess heat capacity is close to 0, or the temperature change is small and can be neglected. So if you assume that the excess enthalpy at T is approximately equal to the excess enthalpy at T naught, then here we go. We have an expression we could solve for T. Okay, and that's it. Sorry about the phone ringing. Hopefully it's not bad.